The GAN model, the GAN framework that was described in this landmark paper started a real revolution in the field with many follow-up papers on applications and improvements of GANs. And in this unit, I want to give you a brief overview of some of the recent developments in this area. It's really a equivalent of Moore's law in this case of AI, where here you can see 4.5 years of progress of GANs on faces in terms of the image fidelity. You can see the original results in the original GAN paper and compare that to results that are obtained today, which are really impressive, and where many people in the community were really shocked that this was possible to generate images with such a high fidelity and such a rich level of detail. The first major step towards image generation with GANs is called DCGAN, and it's basically a systematic search through the search space of possible architectures that work well in this Minimax 2-player game framework. And what they found is a set of basic recipes that lead to models that produce high image quality. For instance, what they did is they replaced pooling layers with striated convolutions in the discriminator and fractional striated convolutions for upsampling in the generator. And we use batch normalization in both the generator and the discriminator. They also remove the fully connected hidden layers for deeper architectures. And they use ReLU activations in the generator except for the output, where they use the 10H. And they use the leaky ReLU activations in the discriminator for all layers. So this was really a very thorough and systematic empirical study on which architectures work well, and because GANs are so notoriously hard to train, it's really important to get these hyperparameters right. So what they showed are samples on more challenging data sets that look much more realistic compared to the original GAN paper. In this case here, samples of bedrooms. Bedrooms are complex scenes to represent with a 2D generative model that operates in the image domain, because there's a huge variety in constellations, in perspective, in appearance of objects inside bedrooms, etc. Here are some examples of random latent code interpolations, where you can see, for instance, that here in the bottom line here, there's a object that appears to be something like a TV is slowly morphing into a window, etc. What they also showed in that paper is that you can do simple vector arithmetics. What they did is they took average C vectors of samples of men with glasses that they have annotated, and subtracted the average vector of men without glasses, and added the average vector of women without glasses, and then added a little bit of Gaussian noise to the resulting latent vector, and they obtained results like this. They can take a man with glasses and remove the man without the glass, and then add a woman without glasses, and you get women with glasses. So there's something semantically meaningful that has been learned. And as already mentioned, there was a real GAN explosion over the last years directly following this original publication. And there's even model zoos that you find on the internet that keep track of the different models that have been developed. One thing that's particularly tricky is the evaluation of generative models, in particular because many of these high performing generative image models that don't allow for exact likelihood computation. And so one of the standard evaluation metrics today, which is not a perfect metric, but it's a metric that's commonly used, is the so-called Fréchet inception distance, FID. And this is a metric used to assess the quality of images created by the generator of a generative adversarial network. And it compares the distribution of generated images with the distribution of real images based on deeper features of a pre-trained Inception v3 network. So the Fréchet inception metric is the Fréchet distance between two multidimensional Gaussian distributions. There's a Gaussian with parameters mu m and sigma m. This is the model distribution. And the distribution of the Inception v3 features of the images, this is the distribution of the features of the images generated by GAN. And this is the distribution of the same Inception v3 features computed over the training set. So if you take the Fréchet distance between these two Gaussian distributions, this is the expression that you will derive. So what happens here, in other words, is that there is a pre-trained Inception v3 network that has been trained on ImageNet. And in the deeper layers of this Inception network, the hope is to find semantically more meaningful features. And if we take these features for comparison of distributions, we obtain something that's much more meaningful than comparing features early on in the network, where the features are much more local and more weak. So this is one of the most commonly used metrics that are used today for evaluating the performance of generative models. And in the original paper where this metric has been introduced, they demonstrated that indeed it does something meaningful. So if you, for instance, if you add noise to the images, then this metric the distance goes up. If you blur the images, then also the metric goes up. Or if you remove certain aspects of the images or manipulate the images or add images from a different distribution, also the FID goes up. So it's a measure of image fidelity and similarity with respect to a data distribution, but it cannot measure or prevent mode collapse. It's not a good measure to tell if the images that are generated from the model are covering the data distribution well or not. One major advance in the field of GAN was the so-called Wasserstein GAN. In the Wasserstein GAN paper, it has been observed that low-dimensional manifolds in high-dimensional spaces often have little overlap, as illustrated here by these two lines. And this is just an example for what happens with image manifolds, let's say. And what they also observed is that the discriminator of a vanilla GAN saturates if there is no overlapping support. So if we have these two modes here with no overlapping support, then the GAN discriminator saturates in these regions because there is no gradients. And so what Wasserstein GANs do is they use the Earth mover's distance instead of the Jensen-Shannon divergence, which can handle such scenarios and which provides meaningful gradients also in the case of non-overlapping support. And this also helps in stabilizing GAN training. Another major advance that has made GAN training more feasible, has led to more stable GAN training and less hyperparameter tuning, is the introduction of regularizers such as gradient penalties. In this paper here, for instance, a very simple gradient penalty regularizer has been introduced that is simply penalizing the gradient of the discriminator with respect to x. And can be shown theoretically that locally this leads to convergence. So you have here, for instance, a standard GAN that is not converging, where the parameters are oscillating. And in comparison here you have two versions using such gradient penalties, where over time the parameters are converging to an equilibrium. Now, a DCGAN with such gradient penalties has been demonstrated to result in high quality samples that are much more high quality than shown in the original DCGAN paper, but without using lots of these hacks that have been introduced to empirically stabilize GAN training. So you can, with a very plain DCGAN network using gradient penalties, obtain samples as shown here in the case of bedrooms, or here in the case of churches. Also note that in some examples here you can even see a little inlay, Shutterstock inlay that has been modeled by the network, because a lot of these images apparently had this inlay inside the images, and so it was remembered as being part of the data distribution. And here are some results on faces. GANs can also be used to translate between two domains, not just to generate an image from a latent code, but to go from an image in one domain, let's say X, to an image in another domain, say Y. And in this paper called Unpaired Image-to-Image Translation using cycle-consistent adversarial networks, this idea of translating between domains has been used, where both a forward and a backward mapping between the two domains, where the domains themselves are the latent variables then, are becoming the latent variables, is trained jointly using different loss functions, a cycle consistency loss that basically measures how well a sample that's mapped from one domain into the other and back into the original domain is aligned with the original sample, and also classical discriminator losses as in GANs. And with this type of models, what we can do is we can take an input image and produce a painting out of it. So we're warping that image from the image domain to the painting domain just by training on an unaligned, unpaired set of images of real-world photographs and paintings of a particular painter with a particular style. And then we can map back from that painting into the original image domain. And there's this reconstruction loss then that tries to make these two the same. You can also recognize there's some ambiguity, of course. So these red flowers here are converted into yellow flowers and they're back converted into yellow flowers. Or here there's a conversion between horses and zebras and back to horses, or between winter and summer and winter, or between aerial photographs and aerial maps and back to aerial photographs, or between facades and semantic labels of facades, or between line drawings and actual photographs of objects. So it's quite fun. You can play with this interactively on some web demos. So here's some more results. In order to further improve the performance of GANs, one idea that has been introduced in this paper on progressively going GANs is to start at a low resolution, train a GAN just at a 4x4 pixel resolution, and then progressively during training add more and more layers to reach higher and higher resolutions, both for the generator and for the discriminator. And with this procedure, they were able to obtain very highly realistic images at very high resolution, up to 1 megapixel, which wasn't possible before. And this is also one of the basic models that is used in the state-of-the-art, the basic approaches that is used in the state-of-the-art GAN models today. Another group of researchers has analyzed how well GANs can scale to more complex data sets. In particular, a data set that is hard to model is ImageNet due to its huge diversity. So we've tried to scale class conditional GANs, where there's a class label that's also an input to the GAN, to ImageNet at fairly large resolutions of 512 by 512 pixels. And they demonstrated that this is even possible without this progressive growing if you have just very large models and large mini-batch sizes, and consequently also large compute clusters. This is done at Google, so it's at Google scale. And they introduced some tricks that are important for making this work, such as orthogonal regularization of G and a latent space clipping. And they explored variants of different regularization strategies, and they particularly analyzed the trade-off between stability through these regularization strategies and performance. And they really found a trade-off there that in the sense that if you include these regularizers, you get more stable convergence, more stable behavior. But on the other hand, you hamper performance in terms of the FID metric. And so what they proposed instead is to monitor the spectrum, the singular values of the weight matrices of the generator and discriminator in order to determine when mode collapse happens, as indicated here, and to stop training at those locations. And they found that this early stopping strategy compared to the regularization strategy of the discriminator leads to better FID scores. This is StyleGAN and StyleGAN 2, which are the state-of-the-art, considered the state-of-the-art GAN models today. And I highly encourage you to have a look at this video, which is really impressive. StyleGAN uses GAN training with regularization strategies, but using a novel network architecture. So instead of a traditional architecture where there's a latent code that's input to a generative model, the latent code in a StyleGAN is mapped through fully connected layers into style codes at different that are input to at different layers in the generator architecture that starts from a constant code. And then there's an additional noise vector that's input also at the different layers. It's injected into this architecture, which allows to control the fine-grained style at different resolutions in that architecture. And with that, what they achieved is to synthesize images that are more realistic than images of any generative model that have been synthesized before. And by changing this input noise that I've just shown, by sampling different input noise, they can obtain very complex stochastic variations. Like in this case, this is this green box here, zoomed in, variations in hair strands, while each of these different variations by itself is coherent and looks natural. So here are some results of this model. This is from the website This Person Does Not Exist. If you go to that website, every time you reload, you will get a new image from that model. And so this is what many people got excited about, the quality of the StyleGAN 2 model in this case. It produces images that are very hard for a human to distinguish from real images unless you're very familiar with this type of models. It's very hard to see the failures of this model. I want to show you some of these some examples of these models here. It produces different types of humans, male and female, with different hair color, beard, non-beard, can produce curly hair, non-curly hair, it can produce glasses, etc.